Hi, good morning. My name is Xavier Bresson. So first, I would like to thank the organizers of the workshop on graph presentation learning and beyond for their kind invitation. So I'm going to talk about benchmarking graph neural networks. And this is a joint work with my students, Vijay Dwivedi, Chaitanya Joshi from NTU, and my colleagues Thomas Lauren from LMU and Yoshua Benjo from Mina. So graph neural networks, GNNs, have become the standard toolkit for analyzing and learning from data on graphs. There is a growing list of applications, including chemistry, physics. So Kyle Kramer will give us, a talk about physics and graph neural networks. There is also recommender systems, social sciences, knowledge graphs, neuroscience, computer vision, NLP, and combinatorial optimization. So actually, there has been a decade of developments of GNNs, starting in 2009 with Sparsity. And then there has been, to my opinion, 3 waves of GNNs. The first wave focused on extending neural networks to graphs. The second waves try to design better nonlinear node aggregation equations. And the recent third class designed theoretically expressive GNNs. Of course, what we want is to develop a powerful GNNs for real-world adoption of graph deep learning. So how do we track progress? The good news is that the field has grown extensively in the last 3 years. But evaluating the effectiveness of new ideas and new architecture has become difficult for 2 major reasons. So first, we, as a community, have been evaluating progress on small datasets. And on small datasets, simple and complex architecture may give you the same performance. Even worse, architecture with no graphs can sometimes give you the same performance. We, as a community, have not rigorously enforced standardized experimental settings for fair comparisons between GNNs. So today it has become critical to solve this issue if we want to develop powerful GNNs. So what we want to identify and quantify what type of architecture first principles are universal, generalizable, and scalable to larger and more challenging datasets. And to do that, benchmarking is a good solution. So for example, in our community, the 2012 ImageNet Challenge has provided a benchmark dataset that has triggered the deep learning revolution. So for GNNs, challenges are developing a rigorous experimental setting for fair comparisons and being reproducible, using datasets that can statistically separate model performance and benchmark distinct fundamental graph tasks. So here's the outline of my talk. So I started with the motivation, then I'm going to introduce you 2 classes of GNNs, so message passing, Weisfeiler-Lehman GNNs. Then I will introduce datasets, infrastructure, and experimental settings. I will report the benchmarking results. And then I will introduce Laplacian positional encodings and link prediction with edge representation, and I will conclude. So message passing graph convolutional neural networks, so MLP-GCN, are the most popular GNNs. So what are the minimal inner structures you need to design a message passing node aggregation function FGCN? Okay, so how do you go from the node representation I at layer L to the next layer? So you need this function to be invariant with respect to node permutation. You need independence with respect to graph size and neighborhood size. You need locality. You also want graph convolution operations. So basically you want to do weight sharing across graph. And you also would like linear complexity with respect to the number of edges, which is going to reduce to the linear complexity with respect to the number of nodes for sparse graphs. Okay. So if I want to satisfy all these properties, at the end, so my update function will depend on the representation at the node I at the previous layer and all the neighbors. So all the neighbors of the node I. Okay, so it's not, we don't have a lot of freedom. The only freedom that we have is the design of this function, but the input of the function will stay the same. Okay, so the first class we designed was what I call isotropic GCN. Isotropic GCN, so here you have, for example, graph sage, update equation. So what you're going to do is that to get the representation of the node I at layer L+1, what you're going to do is that you are going to use the representation at the node I multiplied by W1. And then you are going to use the neighbors of I, so the J, that you multiply by the same weights W2, because it's isotropic. So all neighbors, they will receive the same weight. So these models are, for example, vanilla GCN, graph sage, and ChebNet. But we are limited by the isotropic property here. And remember the standard convnets, so they produce anisotropic filters because, you know, a grid have directional structure. So we know where is up, down, left, and right. But for the original GCN, we just use graph. And if you use a graph, you have no notion of direction. You don't know where is up, down, left, or right on graph. Okay, so how do you get back anisotropy? So you have two options. You can use natural edge feature. So for example, between two atoms in a molecule, you may have different kind of connection, like a single bond, double bond, or aromatic bond. Or you can learn anisotropy, you know, with a mechanism that can treat neighbors differently. For example, with MONED, Getty GCN, or GATT. So here is the general aggregation equation for anisotropic GCN. The only difference with the previous one is that you have this function which depends on the central node I and the neighbors I, and this will be different depending on your neighbor. Okay, so this function can be learned. For example, here this function is the softmax attention over the neighborhood of the node I, and the edge that you have here are learned. Okay, so here this is you know, in modern NLP language, this is the query and this is the key. Okay, so since we are not too far from transformer, what I would like to mention is that in the case of transformer, the neighborhood here, that the softmax here, the neighborhood is done on the whole graph. Okay, so we don't use any particular graph structure with transformer. Everything is connected to everything. Then GCN benefit strongly from batch normalization and residual connection, and it comes almost for free. So you take your favorite GCN aggregation function, then you use batch normalization and you do residual connection. And it is really helpful. You speed up learning process and you improve performance with better generalization. How do you batch graphs with different sizes? What we do is that we first build this sparse block diagonal matrix, and each block is basically one graph, one adjacency graph. And then you do batch normalization along the node direction. GCN leverage graph sparsity. So remember, for NLP, we don't have any you know, topology. Everything is connected to everything, but the topology is very important, right? So we want to leverage this topology because it's a very good inductive bias for generalization. Local computation. So all the computation you see are local and independent of the graph size. Okay. And so it means that this is highly parallelizable on GPU. And you have modern, you know, GNN libraries like DGL, PyTorch geometric, and spectral. So at the workshop, there will be Zhang and Matthias Fade. I will talk about them. That really did a wonderful job as efficient implementation of GNNs. Okay. So the second class of GNNs I'm going to talk are the Weisfeiler-Lehman GNNs. So the motivation here is to characterize the expressivity power of GNNs with respect to the graph isomorphism. So graph isomorphisms means that if you have two graphs like this, so the graph number 1, the graph number 2, actually these two graphs are topologically equivalent. They are the same. Okay, so even if we have a different indexing for the fluorine atom, which is 1 here, and 5 here, we can find a mapping of the index that will match this topology to this topology here. Okay, so these two graphs are the same. The thing is, we don't have an efficient algorithm. We don't know actually if there is an exact algorithm, to check if two graphs are isomorphic. So Weisfeiler and Lehman, they proposed an algorithm to test if two graphs are not isomorphic. At the core of this test, you're going to have an injective coloring function. So this coloring function will take the color of the central node and the color of the neighbors, and will create a new color. So you will apply this function iteratively and get no new color are created, and then you will get a canonical representation of a graph in terms of colors, histogram of colors. If the two histograms of colors are different, then the two graphs are not isomorphic. So the question now is, can we design a graph neural network as expressive as a W test to distinguish non-isomorphic graphs? So that was, the goal of GENE, so the graph isomorphism in a network. And then it's possible to do it if you have a node aggregation equation of this form, where G is an injective function, sum is also an injective operator, and epsilon is irrational. Okay, so it's not easy to define an analytical injective function G, but we can use MLP to approximate it. Okay, it's guaranteed by the universal approximation theorem that it exists such function G. Okay, so we have an MLP here. Then this is the node update equation. Then we can define a graph readout function, and it also must be injective. So you still use again the sum function. So at the end, this is what GENE is doing. So if you have this graph, it's going to map this graph to a space of k dimension. If you have another graph which is isomorphic to this graph, then this will be mapped to the same point in the k-dimensional space. If you have another graph which is non-isomorphic, then it will be mapped to a point which is different. Okay, so this is a pioneering work with the work of Morris on GNN expressivity. Okay, so there is, however, some limitation with the original W test. It is not sufficient condition. So sometimes you have, graphs which are not isomorphic but will produce exactly the same color signature. Okay, and the same also for these graphs. So can we improve the expressivity of the original W test? And if you look at, how we define the original W test, basically we use two tuples of nodes to produce colors. Okay, so we use edges, I and J, for example. So if we want to produce more colors and be more discriminative, then what we need to do is to use k tuples of nodes with k larger than 3. So you're going to use hyper edges like I, G, R, for example. So two tuple of nodes can distinguish non-isomorphic graphs with a 1W or 2W test. Three tuple of nodes can distinguish non-isomorphic graphs with the 3W test. Okay, so now the question is, how do we design a graph neural network as expressive as the KW test? So it was defined by Equivariant GNN, by Lipman and his collaborators. So basically, you're going to have, your input signal, then you're going to have, equivariant linear layers, then you're going to have invariant layers. So all these layers are invariant by index permutation. And then you're going to take, K is going to be the maximum order of this tensor inside inside this neural network. And then there is a theorem that say it exists, a K-order GNN that can distinguish non-isomorphic graphs with a KW test. So this is great. However, it's not practical because K-order equivariant GNN requires, dense tensor of order K. Okay, so and the thing is, if you want to beat GNN with respect to the discriminative power, which is 2WL, then you need at least K equal to 3. So it means that you need a cubic, complexity. So this is quite a lot. So the question was how to design GNN that are 3WL expressive but do not require n-cube memory complexity. So Lipman and his collaborators introduced a GNN to do that by multiplying second-order tensor. together, so n square memory requirement. And but when you multiply two matrices of n square size, then the speed complexity is going to be n cubed. Okay. Along this work, there is also a related method, which is the RingGNN by Bruna and his collaborators, and this has the same flavor. So we want here to multiply equivariant linear layers to achieve higher interactions between the nodes. Okay, so we have a hierarchy of expressivity with respect to the WL test. Here you have the Sparsity GCN, here you have GN, and here you have the 3WL test and the RingGNN test. Okay, graph-agnostic GNN, so this is our baseline. Basically, when we don't use any graph structure, we want to be sure that, when we use graph structure, we want to be sure that we do better than having no graph structure. Okay, dataset. So again, the main issue is the small sizes. What are the ideal datasets? So they must be representative, realistic, medium, large scale size. And actually, this is very challenging to have all these requirements because how do you define the quality of a dataset and also its representativeness? And you also have arbitrary choices. For example, if you do e-commerce, what are the feature you're going to use to define a product and the appropriate size? So when is large good enough? It depends on the task complexity and the statistic of your data. So the recent Open Graph benchmark project is a much needed initiative to tackle these challenges. So Yuri Leskolek will give a talk about this at the workshop. So the proposed dataset, for us, the requirement of the dataset was that we want this dataset to statistically separate the performance between GNNs. That was really our objective. So we have basically medium-sized dataset between 0.27 million to 7 million in total number of nodes, and we cover the 4 fundamental graph tasks, which are graph regression, graph classification, node classification, and link prediction. So the proposed task, so we use Zinc. So Zinc is a real-world molecular dataset, and we regress the constraint solubility, which is an important chemical property when we want to design better GNN, better molecules. We also use MNIST and CIFAR, which are classical image classification datasets that we convert to graphs using superpixel. And for us, they are sanity checks, as we expect, to be close to 100% for MNIST and to do well enough for CIFAR. Then we do node classification task by using the stochastic block models, which is widely used to model communities in social networks. Here we have 2 datasets. The first one is cluster. So we want to identify, communities, and for each community we give only one label. And we have also pattern. So basically we have a pattern that with some feature that we embed in a larger graph, and we want to recognize it. So this is the basic, subgraph recognition task. Then we have also CSL. So this is to test the expressivity of GNN. It was introduced by Ribeiro and his colleagues. They are really highly regular graphs, and you want to be able to classify non-isomorphic graphs. We also have the traveling salesman problem for the link prediction. So basically, this is the TSP solution, and you want to be able to predict, link inside the solution. We also use one dataset from OGB, which is Collab. This is also a link prediction dataset, and the goal is to predict, future collaboration between scientists. So for the infrastructure, quickly, so we have a GitHub repo for that, and our objectives was really to make it as easy as possible, modular, and we have rigorous and fair, experimental comparison. And this infrastructure is built on PyTorch and DGL, so Deep Graph Library. For the experimental settings, so for the data splits, either it is given to us, or we do a random split for the other data sets. For the training, we use a dime optimizer and the same learning rate decay strategy for all GNNs, so we compare fairly. For the statistics, we use 4 different seeds, and we report, mean and standard deviation. For the parameter budget, so our goal was not to find, the optimal set of hyperparameters. We don't have the computational resources. And I think also what we wanted is not to find, the best model for this data set. We wanted to identify, some good principles of building good architectures. So we decide to have 2 parameter budgets. So 100K parameters with 4 layers, 500K parameters with 16 layers, and then we adapt the number of hidden features to fit, the budget. Okay, so let me talk about benchmarking results. So here are the results. It's a big table. So what I'm going to do is that I'm going to summarize the results of these experiments. So result number 1 is that the message passing GCN outperform the w.r.t on all data sets. Potential reasons are so the memory and speed requirement is quadratic and cubic. So it can explain why you cannot scale to medium size. And actually, if you look at Zinc, which is the data set with the smallest graph sizes between 9 and 37 nodes, then this is where the w.r.t performed the best. And I think, this is also an early stage of development of w.r.t. The result number 2, so message passing GCN, they benefit strongly from batch normalization and residual connection. It really boosts performance. It really accelerates training. That's very convenient. For the w.r.t, we were not able to use, we use residual connection, but the performance was not improved, and actually performance is degraded. For residual connection, for batch normalization, we cannot do it because batch implementation is done with a gradient accumulation approach, so it's not clear how you do it. So instead, we try to do layer normalization, which is independent of the batch, and again, the performance is degraded. The result number 3, so anisotropic mechanism improve isotropic GCN. So sparse attention, coming from Badano, or dense attention are not injective, so they are not as powerful as gene, but still experiments show that they are good at generalization. So intuitively, you see that softmax attention is flexible to represent max, mean, and weighted mean with respect to conceptual information, like in NLP. So it's something powerful in NLP. It's also something powerful for graphs. And recent works studied effectiveness of global attention for generalization. Okay, now I'm going to talk about positional encodings. So first, I'm going to talk about structural versus positional encodings. So structural encodings comes from the GCN representation. So GCN, like genes, they are not able to differentiate isomorphic nodes. So they are nodes with the same neighborhood structure. So for example, if you look at the fluorine atom here, it has the same representation as this atom here. Okay, because the 2 nodes are isomorphic. The same also for nitrogen. They are the same representation. Also, these 2 hydrogens are the same representation. These 2 hydrogens are also the same representation. So this is a limitation of the expressivity of GCN. So can we break this structural symmetry? Yes, we can do that if we use higher order WL-GNN, but then you will have to use a dense tensor. Or you can use positional encoding of nodes with linear complexity. Okay, so what are the good properties of positional encodings? So you want a unique representation for each node, and you want this to be distance sensitive. So nodes that are far apart should have different positional features, and nodes which are close by should have similar positional features. One thing which is a limitation of positional encoding is that you cannot assign a canonical representation of positional encoding because of the graph symmetries. And let me explain you that. So let's say I come back with my molecular graph here. So this fluorine atom and this fluorine atom here, so they are both they are structurally symmetric. Okay, so if you decide to assign a positional encoding of A for this node and positional encoding of B for this node, actually it's completely arbitrary. You can decide to switch them. So it can be B here and A here. It's not going to change anything. So positional encoding are always arbitrary up to the number of graph symmetries. So the simplest position encoding you can do is to use the ordering of the nodes among n factorial possible ordering. Okay, so this is one possible ordering, 7, 2, 6, 8, and so on. And then there is a theorem by Ribeiro and his colleagues that you can improve the expressivity of gene by using all permutation of possible ordering. Of course, you cannot do that in practice. So during training, you are going to use, different orderings by uniformly sampling from the n factorial possible choices, because you want your network to be to learn to be independent with respect to these arbitrary choices. Okay, so we introduced Laplacian position encoding. So this is the graph normalized Laplacian, and here this is the eigen decomposition, and you are the Laplacian eigenvectors. So this is an hybrid positional and structural encoding, invariant by index permutation. This is unique and distance sensitive, so this is good. But the Laplacian position encoding have also some symmetries with respect to the sign of the eigenvectors. So you can flip the sign of the eigenvector, and you will not change the eigen decomposition. Okay. The number of possible sign flips is 2 to the power k, and k is the number of eigenvector. In practice, we choose k to be much smaller than the number of nodes in your graph. So it means that the space of sampling 2 to the power k is much smaller than the space of sampling of index positional encoding, which is n factorial. So, but still during training, we will need the eigenvector to be we will need the sign of the eigenvector to be randomly flipped among the 2 to the power k possibilities, such that the network will learn to be independent with respect to these arbitrary choices. And finally, so the Laplacian position encoding are interesting because they are graph generalization of transformer positional encoding. So it gives some light also about transformers. Okay, they are the numerical results. So here CSL was designed by Ribeiro and his colleagues. So they are really highly structured, highly regular graphs. And if you don't use any, positional encoding, then you will not do good. But if you use the Laplacian position encoding, so you will get almost 100%, of accuracy. We improve a little bit pattern, but here cluster is improved a lot, of course, because we know that the eigenvectors are strongly related to the clusters. So of course you will have some improvements. We improve a little bit collab, and zinc has a lot of natural symmetries. So Laplacian eigenvector help a lot, to improve performance. Okay, now I'm going to talk about link prediction. So GCN may fail the link prediction task. So let's say we have this molecular graph, which is composed of 2 identical compounds. Okay, if you apply any GCN, what will happen is that, again, because these nodes are isomorphic, they will produce the same representation. Okay, so this fluorine will have the same representation of this one, and this hydrogen will have the same representation as this one. So when you want to perform link prediction, let's say, for example, there exists a bond between these 2 atoms. And you want to, of course, to predict a bond between the 2 atoms as well. So you will be able to do that. But at the same time, you will also predict wrong links between this atom and this atom here, because they have the same representation, and also between this atom and this atom here. So again, you have some symmetry that you want to break. Okay, so how do you make expressive GCN for the link prediction task? So it was proposed by Ribeiro and Srinivasan. Basically, if you want to maximally expressive, you need to have a joint representation of nodes. And the joint representation of nodes basically is going to encode the distances between nodes. So the thing is that it will require, n square edge representation. So for example, you can see, let's say, for example, that the edge representation is the shortest path distance on graph. So the distance between this atom and this atom is going to be 1, 2. It's going to be 2. But the distance between this atom and this atom is going to be 1, 2, 3, 4, 5. Okay. So you see that you break the symmetry by using, distances between nodes. So what we suggest is instead of using n square, we can use the number of edges by just using, for example, Laplacian positional encoding, which will give you, again, a good distance between the nodes. Also, what we wanted to check is the impact of having a joint representation of nodes when you do link prediction. Is it something that we can see, you know, in the experiments? So what we did is that we try, you know, 3 variations. So the first variation is having no joint representation. The second option is to have an implicit edge representation, which is here. And the last version is to have an explicit edge representation. And you can see that, so for the TSP and collab link prediction, that when you go from no joint representation to joint representation, then you increase significantly the performance of your model. So yes, we need joint representation when we want to perform, you know, link prediction with GCN. Okay, so as a conclusion, my take-home messages are message passing GCN outperform GNN for genes, 3WN and RingGNN on the A dataset using this benchmark. Message passing GCN benefit from graph sparsity, universal building blocks like batch normalization and residual connection, anisotropic mechanism improve isotropic GCN, Laplacian eigenvectors improve index positional encodings, and edge representation with positional encodings enhance link prediction. So there has been, now the community understand, you know, the limitation with WL-GNN, with the dense tensor, and we should use, you know, graph sparsity. So there have been some recent works also presented at this workshop to improve the efficiency of WL techniques. But I think what will be very important again is to be sure that the theory is going to match, you know, practical performances, and we will be able to do that with benchmarking. So just maybe a workshop announcement for next year at IPAM. So we're organizing a workshop on deep learning and combinatorial optimization, and we invite you to participate to this workshop. And I want again to thank everyone for your attention. Thank you very much.